So thanks to the organizers for putting together this meeting. I'm very happy to be part of it, honoring Zoe's contributions. I also have a personal debt to Zoe. She played an important role in my own development as a model theorist. I spent a formative semester in Paris the fall of '99 as a grad student. And Zoe helped with all sorts of practical things, including taking me to the bank and shouting at the bank manager until he relented and gave me a bank account. But mostly she talked to me a lot about difference fields during that semester, and I learned a lot. And my first real paper came out of that collaboration, though Zoe very generously declined to be a co-author. And her kindness support has continued over the last 15 years, and so I'm very glad to have this chance to say thank you. So the work I'm talking about today is very much in the spirit of Zoe's work. It's chalk. So this is a joint project with Martin Bayes and Martin Hils. And it's about the theory CCMA, which is a theory of complex manifolds in the analytic language, equipped with a generic automorphism. So maybe to motivate the study of this theory, let me recall briefly just the basic source of the connection between rational dynamics and difference fields. Okay, so rational dynamics, difference fields. So I'll mean when I talk about rational dynamical system, I'll mean a projective variety over the complex numbers and a dominant rational map. And whenever you have the situation, if you let C of V be the function field, then the dominant rational map induces an endomorphism of the function field just by precomposition, right? So if you're looking at a function, a rational function on V, if we view it as a map to P1, then we precompose with F, and we get F star of J. And so associated to this rational dynamical system, we have this difference field. This is an endomorphism of the rational function, and so we have a field with an endomorphism. And up to birational isomorphism, this difference field determines the rational dynamical system. So to study the birational geometry, at least, of these dynamical systems, one studies precisely the difference field. And then ACFA is the model companion of the theory of difference fields, and so that's the sort of model theoretic in to the subject of rational dynamics. So the question that our work addresses is what happens when V is replaced by a compact complex manifold. So moving from the algebraic context to complex analytic setting, right? So one can talk about a meromorphic dynamical system. As a pair XF, where now X is a compact complex manifold, and F is again a dominant, well, now instead of rational, meromorphic map. Okay? And we want to associate to this more general class of meromorphic dynamical systems some kind of object, like the difference field, that we can then study from a model theoretic point of view. So the first thing already is what plays the role of the function field. So the first thing to notice is that the meromorphic function field, the field of meromorphic functions on a compact complex manifold, is not the right analog, because it doesn't determine the compact complex manifold up to bimeromorphism. I mean, you can have very few meromorphic functions. So if you take, for example, a simple complex torus of dimension bigger than 1, then its meromorphic function field is just the complex numbers. It has no non-constant meromorphic functions. And so taking the meromorphic function field loses too much information. So one answer of what replaces the function field is, one approach is suggested by a model theoretic setting. So let me say something about the model theoretic setting in which we get an analog of the function field. So we let script A be the many-sorted structure. Maybe I draw a line here. Where the sorts are all compact complex manifolds. Well, let me say compact complex spaces, because the smoothness is not essential here. We'll be working bimeromorphically in any case, and so this is sort of a non-singular analog of a compact complex manifold. But for the purpose of this talk, you can think of just manifolds, if you like, compact complex manifolds. And the language L has a predicate for each complex-analytic subset of Cartesian powers of sorts, products of sorts. So it's a very big structure. In practice, one can work with finitely many sorts at a time, but we just consider the whole category where we have a sort for every compact complex manifold. And then we have a predicate symbol for each complex analytic subset. So the complex analytic subsets are given locally at each point in the manifold in an open neighborhood by the vanishing of holomorphic functions. But the structure doesn't have those holomorphic functions as definable functions. It just has the sets, the closed complex analytic sets given as predicates. And so these because of the assumption of compact, induce a Noetherian topology on the compact complex manifold, very analogous to the Zariski topology on a projective variety, of which this is an example. X may be a projective variety. And then we're just looking at the Zariski topology. And I'll use the term Zariski topology to refer to this topology of complex analytic sets. And many of the properties of the Zariski topology are preserved. So in particular, it's a Zariski type structure in the sense of Boris Zilber and Udi Rashkovsky. And so, right, that's the structure A. And then the theory, CCM, is the theory of this structure. So that's the model theoretic context. This structure is very far from being saturated. Every singleton is a complex analytic subset, and so every point is named. And so we need to work in some saturated elementary extension. A prime. So the sorts of A prime are like non-standard compact complex manifolds. Okay. Now, what is the, in this context, we have a natural replacement for the function field of x. Namely, we can let, say, A be an element, a non-standard element. So x is my complex manifold. I can take a non-standard generic point. So this is in terms of the Zariski topology. The topology of complex analytic sets. So I just mean that A is in the sort, and A is not contained in any proper complex analytic subset. Okay? So I take a generic point. It doesn't exist in my standard model, but in the elementary extension, by notarianity of the topology, there exists a generic point. So we take a generic point, and then we can consider just the definable closure of that point. Let me call it B of x, to be just a definable closure of this generic point, viewed as a substructure of A prime. So this B of x is what replaces the function field. It's just a definably closed substructure of this non-standard model obtained by taking the definable closure of a point. So in fact, maybe by QE, you can show that this structure is just the set. We can give a standard interpretation of this substructure. It's just the set of all dominant meromorphic maps from X to other sorts. So here I mean, so when I'm working in the elementary extension, I'll use this notation, the A prime points of X. If I just write the complex manifold, I mean the standard model. So you can look at, so here G is a dominant meromorphic map, and W is an arbitrary compact complex manifold. CCM for compact complex manifold. So other sorts, yeah, all dominant. So if you took W to be P1 of C, the projective line, then you recover precisely the meromorphic function field. Yeah, so the difference is just that the meromorphic function field is not enough. Just looking at P1 of C, you have to look at all dominant rational maps to all other compact complex manifolds. Of course, you then don't get a field. This is no longer a field structure, but it has a structure because it's a substructure of A prime. Right? So you have the structure induced by the language L. So the analog of the difference field, of the function field, is the L structure B of x. And it captures the bimeromorphic, up to bimeromorphism, it captures x. Okay.
So DCL of A equals DCL of B, even on
DCL of A equals DCL of B, if and only if the locus of A and the locus of B are bimeromorphically equivalent. Yeah, so you can also go like this. I took a generic point, but if you take any tuple from the elementary extension, you could look at the locus, the smallest compact complex manifold, the compact complex set containing that element, and this correspondence between is up to bimeromorphism is captured by definability, interdefinability. Yes, that's right. So yeah, so I've gone when I said spaces here, I should say irreducible, reduced. But maybe I should just stick with compact complex manifolds, and by that I mean connected manifolds. So the language of by CCM, I really mean irreducible. Okay, so that's the function field, the analog of the function field, and then of course we immediately get from F this dominant meromorphic map again induces a map from B of x to itself by precomposition. So we get F star from B of x to itself by precomposition. An element, if you think of an element of B of x as a dominant meromorphic map to some other compact complex manifold, then precomposing with F gives us this F star in precisely the same way as it did for the algebraic setting.
Question about Bx. I mean, literally, I suppose the definable closure of A consists of the element Ga.
Yeah. Right. So I'm associating with G. So you're right. I mean, yeah. So this is equal to the set of G of A as you range over all G's, dominant dominant meromorphic maps to W. Yeah, so it's not, yeah. Literally as a set, it's the image of the generic point. But I can just think about these maps instead. And so now it just, yeah, so one should also point out that one checks, it's not hard to see that F star is an L embedding. Where L is this language of complex analytic, predicates for complex analytic sets. This thing feels like it's falling off, but it's okay. Sorry. An embedding. An embedding. I just assumed that this was a dominant meromorphic map, not a bimeromorphism. I just assumed F, yeah? So I'm not actually taking F to necessarily be an isomorphism. You could reduce to this situation where F is actually a bimeromorphic equivalence from X itself, but I'm just assuming it's dominant and meromorphic. So dominant means that it's, so these are all compact, right? So I should just say, yeah, so, but, well, it's only a meromorphic map, so the closure of its image is everything. Okay, and now one has a perfect correspondence then, as one would expect, from this meromorphic dynamical system with this gadget, where this is an L structure and this is an L embedding. Okay? And so instead of a difference field, we now have, I don't know, a different substructure of A prime. So this, should I just send it all the way up? Like that? Maybe we should use this instead. All right. Okay. Right, and so we're led to look at, we are led to consider, from the model theoretic point of view, since we can study meromorphic dynamical systems as these L structures with L embeddings, we should look at the theory of these L substructures with L embeddings. So we look at CCM universal sigma, if you like, which is CCM for all. So this is the theory of the substructures of A prime, together with the sentence that sigma is an L embedding. So this is in the language L sigma, L together with a unary function symbol sigma. So we work in this enhanced language, and we're looking at this, which is something that model theorists have been looking at for arbitrary T, is a natural thing for model theorists to consider. And it was already known, so Martin Bayes and Misha Gavrilovich and Martin Hils had already observed that this theory does have a model companion. So CCMA is the model companion. And so the model theory of CCMA is the model theoretic way to study meromorphic dynamical systems, in precisely the same way that ACFA is an approach to rational dynamical systems. I should say that if you think of the models of CCMA, so let's fix from now on a saturated model of CCMA. So A prime is just a model of CCM, right? So it's not compact complex manifolds, real standard compact complex manifolds equipped with automorphisms, because sigma will always be the identity on the standard model, right? Because it's an L embedding, and L has a name for every element of the standard model. So on a standard compact complex manifold, we're not, it's just it's the identity. On the complex points, if you like, sigma is the identity. It's an automorphism of a non-standard compact complex. Right? So it's a theory of non-standard compact complex manifolds with a generic automorphism. So this going to the elementary extension is essential here. Yeah, it's about the elementary extension. Okay, so.
The manifold is standard, but we take non-standard points in.
Non-standard points in it, right. So by non-standard, I don't mean, well, you also then want to look at closed sets defined over parameters in the elementary extension. But when I write x of A prime, x is defined over the empty set. It's a standard complex manifold, but I'm looking at the non-standard points, right? So we're looking at generic automorphisms of the non-standard points of a complex manifold. Yeah. Oh, right. So yeah. So I should say, yeah. So this is a complete theory because of this, right? So yeah. So this setup is less refined than the ACFA setup because it's choosing a particular completion of ACFA. Yeah.
You start off with sigma in automorphism in the usual sense, and then take all the down, rather than do it with embedding. You start off at the first place with the automorphism,
Yeah.
and then take the complex.
Sure. Yeah. So these embeddings in the model companion will actually be automorphisms. Right? They're embeddings in the universal theory, but automorphisms in the model companion. Okay. So right. So if we view the meromorphic dynamical systems as a generalization of rational dynamical systems, then we obtain CCMA as an expansion of ACFA. So maybe I should make explicit that this really is an expansion of ACFA. CCMA is an expansion of ACFA. So I mean that in the standard model, the complex field is definable in the standard model, on the sort P1. The complex field is a definable field in the model in the standard model of CCM, just in A, and we took an elementary extension of A, and so we got an saturated elementary extension of the complex field. So we have some large algebraically closed field K, and now. If we look at sigma, which makes this into a model of CCMA, then this is a model of ACFA. And in fact, a particular completion of ACFA, namely ACFA with sigma on the complex numbers equal to the identity. Right. Sorry?
The symbols, the elementary substructure symbols.
Yeah, that's true. Have I been doing? Yeah.
No.
This is right. Yeah. Where am I getting it?
A and A prime.
K plus time.
This elementary extension symbol. This here? Yeah. Thanks. I did this also here. Yeah. I'm very sorry. All right. Yes. Okay, so A prime is the elementary extension of A. This is an elementary extension of the complex numbers, a large algebraic closed field, and we get a large model of ACFA, a particular completion. So when I refer to ACFA in this talk, I really mean this particular. I don't mean the incomplete theory. I mean the complete theory where you actually have in the language where you actually have the complex numbers, and they're named and they're fixed by sigma. So it is an expansion. In this sense, yeah. So definable inside CCMA is ACFA. Is that visible? I'll use this. And in fact, one of the things we observe, let me call this theorem 1, is that it's a pure expansion. ACFA is, let's say, purely stably embedded. So the structure induced on the field K, on the algebraically closed field K, by A prime sigma is precisely the difference field structure. There's no additional structure induced on the algebraic closed field. So this is in contradistinction to the case of, say, DCFA. You could look at differentially closed fields equipped with a generic automorphism, DCFA. ACFA is definable there too by looking at the constants of the differentially closed field. But the structure induced by DCFA on ACFA is not the pure structure. But in this case, it is the pure structure. It's just there's nothing other than the difference field structure. So in fact, the way we show this, so let me just say that we get a general criterion. So in any theory T, okay, there's some assumptions, but I'll just state it roughly for now. So suppose S is a sort of T, then S is purely stably embedded in this sense, purely stably embedded in TA, if and only if S internalizes finite covers. So what this means is that almost internality to S is equal to internality to S inside the theory T. So this is a condition about S in the theory T. So there's some assumptions here that I'm not stating. For example, TA should exist. And there's another assumption that I should write down that we don't think is maybe necessary, but that we use. Namely, that sigma restricted to the algebraic closure of the empty set is the identity, which is true in our case.
I mean, SA is still in there, not S. S is
Yeah, S sigma. Yeah, SA. Sure, SA is right. Right. So what I mean is that the full structure induced on the sort S by TA is whatever structure was already on S coming from T together with sigma, together with the generic automorphism.
When you say internality, you mean?
So here I mean, yeah, so almost internality means a type is almost internal to S, means over generic parameters, a realization is in the algebraic closure rather than the definable closure. So almost internality is ACL versus DCL, and internality is DCL, okay? So if they agree for internality, if almost internality agrees with internality, then, and that's something just working in the theory T, in the reduct without the automorphism, that characterizes when SA is purely stably embedded. And so theorem 1 follows from the fact that the projective line internalizes finite covers in CCM, which is well known. So this is the fact, maybe I should state it this other way, that finite covers, let me say it roughly, finite covers of an algebraic variety. Yeah, so finite covers of an algebraic variety in CCM are algebraic. This should be taken with a grain of salt, because by algebraic I mean bimeromorphically equivalent to a projective variety. So really moishazon is the right term. And this is something about the way algebraic geometry is embedded inside complex analytic geometry. So this almost internality is really boils down to this statement, that a finite cover of an algebraic variety inside CCM, so a complex analytic, complex manifold that's a finite cover of a projective manifold, is itself bimeromorphic to a projective manifold. And in fact, we apply this to other cases. So we show, so we also show that simple complex tori internalize finite covers. In CCM. So really, you have to work in the elementary extension. So it's a little bit more than just saying a finite cover. You need this to happen in the elementary extension. So you have a family of finite covers, and you have to internalize. Yeah. So it's really a family of finite covers. So there's a little complication in showing this, but it's quite straightforward to see that this is also true for complex tori. And so we also get an analog of theorem 1 for simple complex tori. Instead of looking at P1, if you look at a simple complex torus, then the full induced structure on it from CCMA is just the analytic structure of complex analytic sets coming from the language L together with this sigma, this generic automorphism. Okay. So right.
From ACL to DCL for P1,
Yeah, I guess it's Gaga that's behind this fact, right? Finite cover is moishazon. I can see, yeah. I guess it's the fact of finite covers because No, yeah, no, it's not. No, that's that projective bundles over CCM. Escapes right now a quick way of understanding why this is true, but taking it as a fact about CCM, that finite covers of algebraic varieties are algebraic.
Some kind of elimination of planetary imaginaries would that count? No, it's not algebraic.
Yeah. We don't see.
Removing finite set.
Oh no, this is something about finite covers, so yeah. Just, right, it's not true in DCFA. Yeah? So this is exactly why this theorem is not true for DCFA. Right. So you have finite covers of the constants in DCF that are not themselves internal to the constants, but here it doesn't happen.
So when you say take it for a fact, you take it also for the in family?
Yeah, it's written down in places, but yeah, so for the model theoretic statement, it appears in model theory papers about CCM, but it follows not too difficult from the standard fact about covers in the base model. But yeah. Okay, now, so what else could we say about this theory CCMA? So some things follow automatically, some things about CCMA follow from work on TA of Zoe and Anand, for example, and also Udi. So let me just list some of these facts that we know. So this is in CCMA. The algebraic closure of a set in CCMA is just the algebraic closure in the sense of CCM of the inversive closure of A. So this is close under sigma and sigma inverse. So we understand what the algebraic closure is. Once you know that TA exists, you get these facts. We get a quantifier reduction. Maybe I won't write it out. Well, let me say it in terms of equivalence of types. The type of A over A in CCMA is equal to the type of B over A if and only if there exists an L sigma isomorphism from the algebraic closure in the sense of CCMA, so say the CCM algebraic closure of AA to the CCM algebraic closure of the inversive closure of AB, taking A to B. This is an isomorphism over A, fixing A pointwise. So we understand what types are. We have a reduction to existential quantifiers of finite covers. Super simplicity. And in fact, we know what non-forking looks like. A is independent from B over E, if and only if the algebraic closure of A. So this is just the algebraic yeah. So maybe I shouldn't. I'll just write it. I've already said that ACLA is given this way. So the algebraic closure in CCMA of A is independent just in the sense of CCM with the algebraic closure of B over the algebraic closure of E. And finally, we also have geometric elimination of imaginaries. So that means that every imaginary is interalgebraic with a real tuple. In this context. However, we show that you really need interalgebraic in the case of CCMA, and this was a surprise to us. So let me say this as theorem 2. CCMA does not eliminate imaginaries. Eliminate imaginaries. And the counterexample that's produced goes via the fact, which Rushovsky has shown, that, that for TA to eliminate imaginaries is equivalent to the theory T satisfying 3 uniqueness. So CCM does not satisfy three uniqueness. I won't, let me not say what free uniqueness is, but just for the people who know what it is, because I want to get through some other things. But this is of itself interesting because a lot of CCM has the feel of various model theories of fields, like ACF or DCF or SCF, but this is something that really separates it. So differentially closed fields, separately closed fields satisfy free uniqueness, algebraically closed fields, but CCM doesn't. And that's why CCMA does not eliminate imaginaries, whether the other theories, ACFA, DCFA, SCFA, do eliminate imaginaries. And the counterexample comes from, it was an idea of Martin Bayes to look at line bundles on K3 surfaces, and it works out, and you get a counterexample in this setting. So, but, right, so I should erase something. So these first two statements are both in distinction with other similar theories, DCFA, for example, and here even ACFA. In one way, CCMA is more tame. In this way, CCMA is less tame. Okay, we were originally interested in meromorphic dynamical systems, so let me get back to that. So in fact, let's look at the following slight generalization. Yeah, so slight generalization. Of a meromorphic dynamical system. Natural one that people do look at. Namely, replace, so remember, meromorphic dynamical system was a compact-complex manifold with a dominant meromorphic self-map. So replace the dominant meromorphic self-map by a meromorphic correspondence. Yeah, finite to finite correspondence. So I'm not sure what a good name for this is, I think, but I'm pretty sure this is not a good name, but we call it a CCM sigma variety. Is a pair, X gamma, where X is a compact-complex manifold, say, and gamma is a complex analytic subset of X cross X, irreducible complex analytic subset, such that when you look at the projections onto the first and second coordinate, pi 1 and pi 2 are generically finite to 1. So over, say, a Zariski open set, it's finite to 1. And so in the case of a meromorphic dynamical system, you would have an F, a meromorphic map from X to itself, and gamma would just be the graph of that meromorphic map. In general, you can replace the graph of a meromorphic map by some finite to finite correspondence. This is natural also to do in the algebraic setting of rational dynamical systems. This is a generalization. Yeah, which somehow, as I will point out in a second, from the model theoretic point of view, is somehow the more robust natural setting to work in. And so by axioms of CCMA, which I never gave you, I just said it was the model companion, so it's a theory of existentially closed difference L structures, right? CCM for all sigma, difference L structures. You get that there exists some A prime point of X that's generic. Whenever I use generic, I mean in the CCM sense, in the redux sense, in the Zariski topology. Okay? So it's not contained in any proper complex analytic subset. There is an A in there generic with A sigma A in gamma of A prime, I guess. This doesn't even use the finite to finite. Okay? And now if you look at, so this is like a generic point, this is like a CCMA generic point of the CCM sigma variety.
Can you state something is generic?
Yeah, so you can, you can avoid, so if you take any, if you look at the axiom, if you look at the geometric axioms, it's, No, but you can avoid any given proper complex thing and then use notarianity to get it. Yeah.
Are they generically finite to one? You really mean generic?
I mean, actually, in that case, you can just take it to be over a Zariski open set. So that you define, over an open set rather than an intersection of open sets. So I say that as generically. Yeah. So I guess in the complex geometric literature, it's distinguished between quotations or not. So quotations means countable intersection of open sets. But it really works off a proper closed analytic subset. The map is finite to one. Okay, so this, of course, you just get whenever you have such a gamma without the finite to one. But what the finite to one is giving us is that the dimension is not increasing, right? So if you look at the dimension, which I mean in the sense of CCM, okay, of the locus. So should I write CCM? Maybe I'll just say it. Dimension locus of A, sigma A. If you iterate sigma on A, say n times, there's nothing that catches the chalk that falls. Yeah, so here I mean both of these in the sense of CCM. So I mean the locus, I mean, as I used it before, the smallest complex analytic set, standard complex analytic set, that contains this tuple as an A prime point. So it's the notion, this risky geometry notion of a locus. And this dimension means a dimension as a complex analytic space. Okay? So these are the standard notions. Then this is just the dimension of X for all n. For such an A, because this is this finite to finite correspondence. So A sigma A has the same dimension as A, because A and sigma A are interalgebraic. They're inside this finite to finite correspondence. And so more generally, we define a type in CCMA. Type, say if A is finite dimensional, we say that a type in CCMA is finite dimensional if this sequence of numbers is eventually constant. Dimension, complex analytic dimension of the complex analytic locus of, well, I guess I should do this with parameters. Sigma n A over A, the sequence is eventually constant. So this corresponds to the notion of finite dimensional type, say, also in ACFA. So it's a transcendence degree type statement. As you iterate sigma, you don't get arbitrarily large complex analytic dimension. And I can work over any parameters in the elementary extension. So when I've been talking here, working over the empty set, right? X was a standard compact complex manifold, but this definition can be made. Locus makes sense even in elementary extensions. Dimension makes sense in elementary extensions because it's a definable property of parameters in CCM. So these notions also make sense over parameters, even though I've only really explained them, not over parameters. So those are the finite dimensional types that they don't grow as you look at prolongations. The dimensions don't grow as you look at prolongations. And the usual arguments show that they correspond up to interdefinability precisely with CCM sigma varieties. Okay, so the study of finite dimensional, so these correspond up to interdefinability with CCM sigma varieties. Of course, I need to make the definition of a CCM sigma variety over parameters. So the definition I gave was just CCM sigma variety over the empty set. You can make a definition over parameters, and then the finite dimensional types are precisely the types arising in this way. Yeah, the type of A, where A is such a point, a generic point of the CCM sigma variety, landing inside the finite correspondent. Okay. This is okay. Can you do two at the same time? No. Okay, so the study of, if we're interested in meromorphic dynamical systems, or more generally CCM sigma varieties, so meromorphic dynamical system is an example of a CCM sigma variety, then it's the finite dimensional types that one needs to study. And so what we prove, the main theorem, which I'll state now, is the Zilber dichotomy for finite dimensional types. So our main theorem is the Zilber dichotomy. So maybe I should, I'll state it over parameters. So if I have a type over some parameters, say algebraically closed set of parameters, which is finite dimensional, and of SU rank 1, then P of x is either 1-based or non-orthogonal to the fixed field. And I really mean the fixed field of ACFA, the fix of k plus times sigma. Right, which remember is definable inside CCMA. So in CCMA, you get no new non-1-based U rank 1 types of finite dimension. They're all coming from ACFA, but in fact from the fixed field. Yeah? So this is the analog of the dichotomy in ACFA stated for CCMA. And so this somehow should this encodes some properties of CCM sigma varieties, and hence of meromorphic dynamical systems. But for the rank U rank 1, this is a statement about U rank 1. It doesn't, no. So we give you have examples of infinite dimensional, but U rank 1. Yeah. So this, I guess the same is true in DCFA, right? The SU rank 1 does not imply finite dimensional. So that happens here as well. So this is proved by what is now a standard procedure, strategy. What we actually prove, so this follows from the canonical base property. So let me state that, a certain canonical base property for CCMA. So let me state it let me just state it over the empty set. So you can state it as something about CCM sigma varieties. So I have a CCM sigma variety. You can say it about finite dimensional types, but via this correspondence, let's state it for CCM sigma varieties. And let's take A in X generic, such that A sigma A is in gamma, which we know exists. So a generic point of this CCM sigma variety. And let's take some other set of parameters. So B is some algebraically closed set of parameters in the universe, A prime. And E is the canonical base of A over B. So this is an element really in A prime sigma EQ, which is not, it doesn't eliminate imaginary, so it's not necessarily a real tuple. It's potentially an imaginary tuple, but we do have geometric elimination of imaginary. So up to interalgebraicity, you could take E to be in the standard model. And then the conclusion is that this has no U rank 1, right? So this is the more general statement about finite dimensional types, right? This is a finite dimensional type because it comes from a CCM sigma variety, but no U rank 1 assumption. And then the conclusion is that the type of the canonical base over a realization is almost internal to the fixed field. Okay, so that the CBP implies the dichotomy is a general argument that stems from observations of Ahn and Pillay about stemming actually from the theory CCM. So we're applying these arguments back to, well, some expansion of CCM. And the proof of the canonical base property itself is a jet space argument, like the work of Anand and Martin in DCF and ACFA, right? So you get the canonical base property by defining an appropriate notion of jet spaces, and yeah, so this is this is proved by by developing an appropriate notion of jet space, as in the paper of Anand and Martin. Yeah, sorry. Did you?
If you have an element which is in the definable closure of a finite dimensional element, is it also finite dimensional?
If it's in the algebraic closure of or definable closure, yes, yeah. So finite dimensionality.
Could we not replace then the U-rank 1 condition by finite U-rank and then do an analysis?
Yeah. So this is right. So each step of the analysis will either be one-based.
But there must be no formula. I mean, both conditions. I mean, you can't make it separate the analysis so that eventually you have one false.
Yeah, as in like Zoe's general theorem that yeah. Yeah, I guess something like this is possible, yeah. But yeah, so I'm thinking of this as just each step in the analysis, either one base or non-orthogonal. But I suppose you can split P up into the part that comes from the one base. I guess, I'm not sure, yeah. Actually, I'll stop there. Yeah. Thanks.